So my name is Xiaolin Zheng. I'm in mechanical engineering. I will be the section chair for this afternoon. Let me start with my favorite slides. This one really shows the energy resources in kind of a circle pie chart. On the far right-hand side shows those fossil fuels. And the size of each circle shows what's known reserve for each fossil fuel. For example, on the top, we have natural gas, petroleum, uranium, and the coal. On the left-hand side, the other circle shows the energy resources from renewable energy, and the size shows the yearly supply. And you can see the dominant one is the solar. And on the very far left corner, there are two small circles with the Earth's graphic on top. One is the annual consumption of our energy in 2010, and the other one is predicted in 40 years, 2050. So you can see solar is a very significant part of our energy structure. Actually, if we count the energy input from sunlight, every hour the energy we receive from sun is enough to power us for more than a year. According to Nobel Prize winner Richard Smalley, he said, we are best in energy. So this is the session is about solar energy, and we have seen tremendous growth in PV in the past 10 years. Here shows the PV global capacity from 95 to 2012. And you can see within 20 years, the PV capacity has increased by 100 times from almost 0.2 gigawatt, 0.6 gigawatt to about 100 gigawatts. And the almost 10 times increase happened in the less than 10 years. From 2007, the capacity increased about 10 times. So we really see this dramatic increase almost simultaneously with GCEP for the past 10 years with this PV increasement. At the same time, the price of PV also drops dramatically. If we start from 1977, here shows the peak price about $76 per watt. And now it's about 100 times cheaper. It's about 74 cents per watt. Again, about this 100 times change, about 10 times change occur in the past almost 7 or 8 years, again coincide with the GCEP. So this really shows the importance of solar cell. Although the solar cells has progressed dramatically in terms of the capacity and the cost, there's still a lot of research to do in solar cell. If we look at solar cell, the basic one shows it absorbs light, generate carriers. So you need to absorb enough light and also to collect all the carriers. And this session is really focusing on the light harvesting perspective. So all the research is really focusing along this solar spectrum. On the very top, we have this sunlight. It radiates like a black body around 5,000 degrees C. After sunlight passing the atmosphere, we have this, the right part shows the solar spectrum. So for solar cell, researchers are really trying to harvest a broad spectrums of sunlight. And within the range they can absorb, they're trying to absorb maximum, almost 100% of the sunlight. And then one of the talk will tell you solar cell not only absorbs energy, it also radiates energy, and that will lead self-cooling solar cells. So that will bring us to these three exciting talks by world-renowned scientists on this sunlight or radiation part. The first talk will be by Professor Mark Brongersma, and he is a professor in the Department of Material Science and Energy at Stanford University. He leads a research group directed towards the development and the physical analysis of new materials and the structures that use in nanostructured electronic and photonic devices. His recent work focused on solar energy harvesting devices, light resources, etc. He is a PI for almost 4 GCEP research programs. He received his PhD in material science from the Foam Institute in Amsterdam, the Netherlands, in '98. And from '98 to 2001, he was a postdoc at Caltech. And now we'll welcome him to talk about nanophotonics for solar energy harvesting.
Thank you so much. It's a real pleasure to be here and discuss a little bit about the work that our group does in using nanophotonics for solar energy harvesting. And as my presentation comes up, I'll just discuss, yeah, that's the one, say that I'd like to, I guess, give a little bit broader perspective than the research that we just do under GCEP. I guess we don't have slides yet, but okay, good. Under GCEP, to give a little bit more broader perspective, how we use nanostructured materials, metals, and semiconductors to manipulate light at the nanoscale to make a variety of different optoelectronic devices. And of course, I'll focus on the work that's done under GCEP. Before I start, I want to acknowledge many students that contribute to the works that I'll be discussing. Also, GCEP as a very loyal sponsor to many projects in our group, but I'll discuss a couple projects that are also linked and fed into GCEP work. And I also want to acknowledge many great collaborations with groups at Stanford, such as those of Bruce Clements, Mike McGehee, who is one of the speakers here, Yi Cui, Aris Husman, and Ming Qiu. So, the key message that I want to convey today is that as we nanostructure metals and semiconductors at the true nanoscale, at scales that are much smaller than the wavelength of light, we can try and make a big impact on manipulating light absorption, light transmission, and light reflection. And in doing so, we can fundamentally alter perhaps the way that solar cells are going to work in the future. But let me briefly back up and mention that light is used in many optoelectronic devices, such as cell phones, photo cameras, solar, lasers. And if you take a cross-section of some of the devices and look inside, you'll notice that many devices, here are some of the devices you just saw, for example, a solar cell, are consistent of many layers of semiconductor material that are doped in various ways, and also often metallic back reflectors. And the key question I want to pose is, what would happen if we nanostructure the metals and semiconductors inside such optoelectronic devices? Could we boost the efficiency? And I'll show various examples that show that there is a real opportunity here. So let me give you one trend in solar cell research, and this is plotted along a length scale, whereas we're used to, for example, beautiful silicon crystalline solar cells that had textures that were many wavelengths in size. Here's one with a 10-micron scale bar to try and trap light in many hundreds of micron crystalline silicon solar cells. We're trying to now go to extremely thin solar cells, where the thicknesses are maybe just on the order of 10 microns, or perhaps even thinner. And we use different types of nanostructures, like this work from Albert Pullman's group, silicon particles that are on the order of 100 nanometer in size, to trap light in such thin layers. So interestingly, in making this transition on this length scale, we have crossed an important wavelength scale, or size scale in optics, which is the wavelength scale of light. And as a result, the way light interacts with these materials is completely changing. Just to give you two commonly known now examples of metals and semiconductors, when you buy a piece of metal wire or a mirror in the hardware store, or look at a silicon wafer, they look nice and shiny when polished, when they're big compared to the wavelength scale of light. But as you break them up into nanostructures, metallic particles or semiconductor wires in the size range of a few tens of nanometers to a few hundreds of nanometers, you notice that when you shine white light on them, they have very different colors. The metals can be tuned in their light scattering and absorption properties all across the visible, and the same holds true for semiconductors. So by controlling the size and shape of metals and semiconductors, we can alter the way light interacts with them. So can we use this to make real planar technologies? Well, we're trying to follow a simple pathway, and that is first use our knowledge of breaking up these metals and semiconductors into nanoscale building blocks, and then use these building blocks to go back up and to make what are now known as metamaterials, basically nanostructured metals and semiconductor materials that, for example, if we pattern a metal with a series of grooves, we can change the way light reflects off of it. Or if we pattern semiconductor films into different beam sizes of silicon, we can generate different colors showing that we can control light absorption and reflection properties by a simple nanostructuring step. So let's see how we can use this. And first, I want to acknowledge an enormous amount of work that has been done in the microwave in nanostructured metals and also semiconductors. Here's work from Eli Jablonowicz and Nader Engetta's group about a decade or so ago. People found that if you, for example, just dig an array of grooves into a metal film, where the size and the spacing of the groove is small compared to the wavelength of light, you can manipulate the reflection of light. And interestingly, if you have this distance be much smaller than the wavelength of light, you avoid first-order diffraction. The only thing the light can do is to come in and reflect. That sounds extremely boring, and you wonder, why is this useful? Well, it turns out we can, upon reflection, change the reflection phase of the light. And as you change the reflection phase, you change the standing wave pattern of the light coming into the mirror and reflecting of it. You can change exactly where your maximum of the field intensity are, and thereby where the strongest light absorption or light matter interaction will take place. Also, people have made more and more complex structures, fractal structures, little oscillating lines and things that here at the bottom line change the different of, these are metallic nanostructures on a surface, change either the shape or orientation along the surface. And it turns out that if you shine light on such structures, you can redirect the light like a grating or focus the light, and I'll show some examples of that. So simple nano patterning can do a lot with light reflection. So if you look at any type of solar cell, whether it's a beautiful single crystal solar cell or an amorphous silicon or a gallium arsenide layer cell or an organic cell that's made in Mike McGehee's group, then you can see that all of these solar cells have in common that there is a metal that serves as a charge extraction electrode, but also something that reflects the lights and gives it one extra path through the solar cell. So what about manipulating the reflection of the light where it comes in off of this mirror to enhance efficiency? Well, to see that this can make a big impact, I have a little simulation here that's very simple, where light comes in onto a perfect electrical mirror. So think of a high conductivity silver or aluminum mirror that's in a solar cell. And if you plot the electric field, think light intensity, in front of this mirror, you can see a standing wave pattern in front of it, because there's a wave coming in, a reflected wave. These together produce a standing wave pattern, but because of the high conductivity of the metal, the reflected wave has an 180-degree or pi phase shift. And as a result, there's destructive interference of the fields right at the surface, and the light intensity is very low. So if I would try and make a very thin solar cell, indicated here by a pink absorber layer, I only tap into this very low field intensity. So we're trying to see what we can do. Well, we could, for example, move the absorber layer to the peak of the field intensity, and then what people have done in the past is to insert a conductive and transparent spacer layer like indium tin oxide or tin oxide, something that's nice and transparent and spaces the charge producing layer away from the metal so we can still extract the charge. But materials like indium tin oxide are not, all the elements are not earth abundant, and they're expensive, and there's also a little absorption. So wouldn't it would be nice to change the mirror itself? So in the microwave regime, people have changed things from things like electrical mirrors to magnetic mirrors. And interestingly enough, an electric mirror, upon reflection, flips the electric field, producing this low intensity right at the surface of the mirror. But if I make a magnetic mirror, I can actually flip the magnetic field and keep the electric field in the same direction. So if I want to make a thin organic solar cell, for example, that's thin because the charge transport is relatively poor, then I can take advantage of this high field right at the surface. And here's one simulation of this. Here's a conventional mirror. Here's the simplest grooved a magnetic mirror where you come in with light and you reflect. If you make little grooves orthogonal to one polarization direction of the light, it turns out that the electric field has a harder time driving currents along this surface. Now these electrons need to go up and down into these little grooves, and therefore you can change what is called the surface impedance, how easy it is to drive currents in the material, and change the reflection phase. And here you can see a simulation of a grooved surface here at the bottom, light wave coming in, and you can see now the first high standing wave maximum is right on top of these, what are in blue, these metallic teeth. So if I have a thin layer, it could be graphene or it could be a thin organic solar cell, I can tap into this high field to get the maximum light intensity. And here's one cell that we made in collaboration with Mike McGee's group, where we basically took a metallic film, dug sub-wavelength grooves with sub-wavelength spacings in a metal. His group was able to put an organic cell on top with a transparent electrode on top of that. And here we measure the enhancement in the photocurrent versus wavelength of illumination. And we can see here a broad enhancement of a few tens of % over a broad range of wavelength in the photocurrent in the region where we made the grooves inside the metal. So simple step of making grooves can significantly enhance efficiency. Another example that I want to give is to nanostructure the semiconductors themselves. And there's lots of work. Here's some history of making or analyzing how light interacts with high refractive index semiconductors. Starts with the work of Gustav Mie. And already in the 1940s, people made metamaterials, not termed that way, of dielectric spheres embedded in other transparent lower index media. And since maybe the 80s, people have started developing real antenna structures like the metal wire you had on your car or the Yagi-Yuda antenna to receive TV. These things were also made in dielectric structures like silicon to try and better receive, in that case, RF radiation. But now the question is, can we also receive better solar visible radiation to make a better solar cell? So lots of work has been here in the recent decade. Here's tuning of the light scattering of just the silicon wire in the range of 30 nanometers to 180, no deep sub-wavelength, just a few tens of nanometer. You can tune the color of the scattering. If you want to trap light at all wavelengths of the sun, you may want to use this tunability. Also, if you tune the length of a silicon wire, you can tune the color. And it turns out that any cross-sectional shape, this is beams of silicon, that's square, circular, hexagonal cross-section, all of these show resonances where effectively the light circulates inside the high-index material, silicon, by total internal reflection, to give higher field intensities inside these structures than around them. So if you want to think about how much light could I achieve in just a very thin layer of material, there are interesting papers on this topic by Woltersdorf and Salisbury in the United States and in Germany that showed that if you have a thin freestanding film, it turns out if you change the sheet conductivity or optical properties of this material, you can get exactly 50% absorption, fundamental limit for a freestanding film. If you take that film and put it on a metallic back reflector, you can get unity absorption in a layer that ultimately is just a couple nanometers in thickness. So we were hoping to look for this and found this paper by Federico Capasso, who showed that if you have germanium films on the order, which is this image on the left, on the order of just 10 nanometer on a gold back reflector, you can get very strong absorption that's tunable by the film thickness, and all the different colors that you see here are germanium layers gold that are just a few nanometers in thickness different, and they give their color due to the light absorption of the complementary color. So we did some simulation to see how far you could push this, and this is a simulation here on the left that shows that just for a 12 nanometer thickness germanium layer, if you plot the absorption versus wavelength, you can get unity absorption here at about 600 or so and a little bit nanometers, where 98% of the absorption takes place usefully in the germanium layer itself and 2% in the metal, and it's quite broadband and extremely omnidirectional. So if any direction you shine light on it, it will get nicely absorbed in this layer. So there's a simple origin for this. Germanium is such a strong absorbing material that if you look at the light coming into a germanium film that sits on a silver back reflector, light can take two paths. It can reflect directly off of the germanium or go in, circulate a little bit between these interfaces, come back out. And if these two pathways are equal in amplitude and opposite in phase, they will destructively interfere, and the light has nowhere else to go than be absorbed in this germanium layer. So there's a well-defined resonance condition for this. But as my colleague mentioned, Shanhui Fan said, this is very nice, but actually we need absorption across the entire bandwidth of germanium. And that set us off on a quest to try and nanostructure this germanium layer. So here's another example where you can see the impact of nanostructuring. In this case, a 50 nanometer germanium film. In this schematic, we have a germanium film. We pattern it in two beams. Here is a scanning electron microscopy image. The size and spacing of these beams is below the wavelength, so there's no diffracted orders. The only thing that light can do is come in, be absorbed, or come back. And you can see here, just as an illustration, what happens if the electric field is polarized normal to the length of the beams or along the beams. You can see here optical images, just reflection of white light. Here's the germanium film sitting on gold. Here's the gold background. Germanium looks reflective. If you polarize it orthogonal to the beams, there's no strong resonance driven in the germanium beams, and you see the gold underneath. But if you align it along the length of these beams, you see that this film almost looks black. So you can get very strong light absorption, which is interesting. By removing material from this continuous film, we get stronger light absorption because we drive a resonance where light circulates inside the germanium a little bit longer than it would in a uniform film. So here are a couple simulations. Here, this is the case where it's orthogonal. Then the light doesn't drive resonance. It just hits. This is the power flow. These lines hits the metal film. Some hits the germanium, gets absorbed. But if you look at this black film, interestingly, despite the fact that there's a significant spacing between these germanium beams, you can see that the light comes in and ultimately right near this, within about a wavelength from the structure, funnels into this structure, very similar to a conventional antenna effect. So this beam can grab light from an area that's big, maybe 4 or 5 times ultimately the size that the structure has itself. So light doesn't have to go in a straight line in the near field of these structures. And you can get, for one beam, you can get very strong broadband absorption. And interestingly, the peak of the absorption is exactly determined here. This vertical line is where an individual beam without neighbors would absorb most strongly. So we now can, because we know that this metamaterial consisting of many sub-wavelength beams shows strong absorption exactly at the resonance of the individual beam, we can use all of our knowledge that we developed of understanding the resonances in individual beams to try and make more complex metamaterials. And here's one interesting example. What if we had two beams that at some wavelength grab all of the light from an area that's much bigger than the beam size itself? Then we can stick smaller beams in between that could resonate at a different wavelength. If I make a surface of big, small beams, then I can get absorption, hopefully, at the wavelength where the big and the small beams resonate. And this is indeed the case in simulations and experiments where you can see that if you make samples with just big beams or just small beams or a sample with big and small beams, you can see here the reflection spectra, which are one essentially minus absorption. Just small beams gives you a very strong reflection dip, so strong absorption at short wavelength. The red curve gives you what just the big beams absorb. They absorb more at long wavelength. And if I have big and small, I have 2 peaks. So I can try to further engineer this to maximize absorption over a broad bandwidth. So currently, we're actually making devices out of this. Here you see a cross-section where we have big and small beams of silicon, which are going to laterally split. Red light will go into the big beams, blue light into the small beams, and the hope is to put ultimately different semiconductor materials there to not do spectral splitting in layers below each other, but in a plane. And this plane is going to be just on the order of about 100 nanometer thick or smaller, and will hopefully absorb all the light. The last minute I want to discuss on a completely new technology where we now are going to spread out the strong silicon light scatterers and absorbers over large areas. And the hope is to see whether we can take conventional lenses that are typically large, but could be used for solar concentration, to try and that nicely focus light in a conventional way, to try and place many silicon beams into a just 100 nanometer thick layer, and to see whether that can have the same action of concentrating light. And interestingly enough, it does. Here you see an optical lensing element. It contains, if you look carefully, of a couple tenths of thousands of silicon beams. And the simple idea here is that each of these beams can control this light scattering amplitude and phase, and thereby control the wavefront as it passes through the structure, and it allows focusing of light. Here you see a simple experiment of this structure. Well, here's the schematic of the illumination. This sits in 100 nanometer polycrystalline silicon film on glass. You shine light on it, and here's the experimentally measured focus, and you can get to a diffraction-limited spot size. So we're trying to build these elements for light focusing. We're trying to, here you see an example of a grading structure that could replace a highly textured surface, and we can nicely take such very thin films to redirect light inside a solar cell and enhance efficiency. Currently, we're at diffraction efficiencies of maybe in excess of 70%. So this is where I want to stop and leave you with this slide and say there are many optoelectronic devices, most notably for our group, solar cell devices that are built out of many layers. And there's an interesting question if we can re-engineer these layers, pattern them into nanostructures at the cost of having many additional problems in surface passivation, electrical challenges, but there's a great optical opportunity to manipulate the light absorption and the reflection in such devices to try and boost the light absorption and achieve unity absorption in just sub-100 nanometer thick semiconductor solar cells. So with that, thank you for your attention.
Now the floor is open for questions.
There's one over here.
John Massey. What do you think are the biggest barriers you've got to making progress in this? That is, what do you wish for most?
Well, I guess I mentioned briefly one challenge, which is surface passivation. So by nanostructuring these thin films, often we see very clearly all of the optical effects, only reduced in efficiency, because by nanostructuring these materials, we create more surface area where surface recombination can be created. So there are new types of solar cells, like these perovskite solar cells or other solar cells, and beautiful work from our chair on passivating nanowire solar cells, but that's definitely a challenge. What my goal is here to show that it's worth maybe looking at this surface passivation more, because there's a real optics opportunity.
Yes.
I don't know if you mentioned that, maybe I missed it, but what are the efficiency improvements that you can get about, with any of these schemes?
So the efficiency, or I guess there are different ways of thinking about it. One that we're really after proving is that we can go perhaps from a few hundred micron thick crystalline silicon solar cell and do the same light absorption in a nanostructured cell that's maybe ultimately, well, we can push it, I think, to about 100 nanometers, but probably practically a cell may still be about 10 or so microns. So there's a significant possibility in thickness reduction if you're allowed to nanostructure your materials. And for example, my colleague Yi Cui has developed many interesting nanostructuring techniques, and he's been helping us try to see whether we can apply some of these concepts in real solar cell materials.
The people who use, for example, gallium arsenide,
yeah,
they got up to 29%. So is that?
So there's also, of course, the power conversion efficiency. So some of the, that's an excellent question. So I think some of these material systems, like crystalline silicon and gallium arsenide, Alta cells or SunPower here, they have cells that are extremely close to the ultimate efficiency limit. So we're not, I think, going to boost these efficiencies. We're going to hope to achieve these efficiencies in much thinner and hopefully, ultimately, with new nanopatterning techniques coming online, cheaper cells.
Other questions? Yeah, over there.
How is the local temperature? How's the more extreme local temperature rise in these smaller structures factor into the structure of the whole device? Yeah,
so we don't have complete answers to that yet. But there are, interestingly, two competing mechanisms. So in the thinner cells, we essentially do solar concentration, which is another potential opportunity to boost efficiency a little bit. But at the cost of solar concentration, there will be more recombination-induced thermal heat generation. But interestingly enough, the semiconductor materials where you have this solar concentration also sit closer to a metallic surface. So it's very much going to depend on what solar cell material you're using, whether and what thicknesses you hope to scale back from, whether it's a positive or a negative.
Yes, over there.
We have more.
Thank you. I have a question. As I know, for the commercial silicon solar cell, they already have some texture structure, like reversed pyramid structure, and they already have the light absorption. So what's the difference and what's the advantage of you? Did you compare these results at your result and the commercial ones?
Yeah. So again, I think we're not going to beat the efficiency of commercial cells. We're going to try and, we're probing whether it's possible to make them thinner and achieve similar efficiencies. But interestingly enough, as you go from hundreds of micron, maybe crystalline silicon cell, to a cell that's maybe 1 to 10 micron in thickness, typically the type of structures that are most effective are no longer the big, for example, pyramidal structures, because in that case the texture is about as thick as the solar cell itself. You want to use smaller sort of designer nanostructures to put there that are on the order of a couple hundred nanometers, small compared to the wavelength of light, and then you have to use, instead of ray optics, wave optics. And Shanhui Fan, who will be our next speaker, has a lot of very nice papers that discuss the physical nature of this transition and going from ray optics to wave optics, where we, instead of following rays, refracting them, we use these resonances in metallic and semiconductor structures to enhance efficiency. So yeah, there are many fundamental differences in trying to optimize such cells as well.
Yes, question to her.
Quick question, maybe you mentioned it. Your light source, polarized or unpolarized?
So that's an excellent question. So thank you for asking, actually. The structures I showed you were linear structures. Interestingly enough, the semiconductor nanowires, if you design them correctly, they can show resonances both for the electric field normal or along the wire structure, and therefore could take unpolarized sunlight. These mirrors that I showed you, they are polarization dependent, but it turns out that a simple cross pattern already can be made polarization independent and do the same physical action. So it is definitely, although these were good for educational purposes, it is possible to use an unpolarized source and get the same efficiencies.
Yeah, last question.
You mentioned spectrum splitting a bit. Are there good prospects for using these structures for multi-junction cells?
Yeah, so I think it's I guess we're just at the beginning here, showing that you can take structures that have resonances at different frequency, put them together in a sub-wavelength spacing, and there will be a natural energy sorting of red into one, blue into one. And so you can, laterally, spectrally split, probably in 3 or 4, I would say, different types of semiconductor materials. So with that, the efficiencies you can achieve, I think, are very similar to ultimate efficiencies of layered semiconductors, where you have 4 different types of bandgap semiconductors on top of each other. Only now you have the additional advantage of solar concentration laterally into the different structures.
Yeah, with that, I thank Professor Mark Brongersma.
Thank you.
Yeah. So let me introduce the second speaker for this session on solar and radiation energy conversion is Professor Shanhui Fan. Shanhui Fan is a professor of electrical engineering and the director of the Edward Ginston Laboratory at Stanford University. He is a principal investigator on the GCEP efforts, high-efficient thin-film solar cells using nanoscale light management and nighttime radiative cooling, harvesting the darkness of the universe. That will be the title of his talk. His research interests are in fundamental studies of solid-state and the photonic structures and the devices, especially photonic crystals, plasmonic, and metamaterials, and applications of those materials in energy and information technology. Fan is a recipient of NSF Career Award, a David Luca Pickard Fellowship in Science and Energy, the National Academy of Science Award for Initiative in Research, and Adolph Loeb Medal from the Optical Society of America. And Fan earned his PhD in theoretical condensed matter physics from MIT. So thank you and welcome.
Well, thank you. So I'd like to talk about some of our work, a slightly broader perspective of some of our work in trying to do radiative cooling. So as way of a background, we're talking about renewable energy resource here. And so it will be interesting to examine the basic thermodynamic resource that's available to us. Certainly, there's the sun, and Professor Zheng talked about, which is a fantastic energy source. On the other hand, if you just go out and look away from the sun, and if you imagine that the sun is not there, then you should see the dark universe. And the universe is extremely cold. This is at a temperature of 3 Kelvin. Now, from a basic thermodynamic point of view, something that's cold is also extremely important as well. If you think about just the Carnot efficiency conversion limit, it certainly will be great if all the energy conversion process that's currently going on do not use the Earth as the heat sink, but use the universe itself. So what we would like to do here is to point out a pathway towards harvesting this thermodynamic resource that really has not been very widely discussed. Now, one of the very important points about photonics that we all pursue here is that it provides remote wireless access to thermodynamic resource. None of us doing solar cell research actually sit in the sun. So by the same token, you actually do not be sitting in outer space to benefit from the existence of it. And the black curve here is the measured transmission spectrum in Hawaii, actually, of the atmosphere. It's a fairly complicated spectrum, but I'd like to draw your attention to the wavelength range between 8 to 13 micron. And that wavelength range here, the atmosphere is very transparent. And that happened to be at the peak of the black body radiation spectrum for a black body at 300 Kelvin. So another way of saying it is that if you step outside, you are actually radiating heat into outer space, every one of us. And so that's a mechanism that potentially can be used for cooling purposes. And in fact, there has been a technology that's been around called nighttime radiated cooling in precisely trying to do this. And what they do is they take a black radiator, anything that looks black, like a carbon black radiator would do. You bring it on the roof at night, have it face the sky, surrounded by an insulating material. Now the heat is going to be radiated into the sky, and therefore the radiator will have a lower temperature. It is actually a fairly straightforward experiment, and we could do that easily here at Stanford to show that in doing so, you can get a temperature about 10 to 15 degrees Celsius below ambient. This is a technology that has been around actually for a long time. Some of the early papers dates back to even the 60s. But what we are seeing is a very important opportunity that have not been addressed, where one can use photonic technique and concept to drastically improve the performance and widen the range of application that you can think of with this kind of radiative cooling concept. So in this talk, I'm going to talk about three separate things. I'm going to talk about our work on daytime radiative cooling. We're then going to show how to combine radiative cooling with solar cell. And finally, I'm going to talk about some of the latest results that we have in the GCEP project, where part of the project was to try to push the limit of nighttime radiative cooling. So let me start with the daytime radiative cooling. The experiment that I showed you was carried out at night. Now, if you care about cooling, of course, you would like to do it when the day is hotter. And that's probably around now when the sun is shining. You probably would not imagine to put a piece of black carbon and go up to the roof right now to see any cooling. And the reason, of course, is a very simple one. The sunlight heated up. So with that notion, then the concept for daytime radiative cooling actually is a fairly straightforward one. What you would need to imagine is a structure that has an emissivity or absorptivity spectrum that looks like this, that it reflects all the sunlight so that it doesn't get heated up by the sun, but it strongly emits in the 8 to 13 micron window. And remarkably, that kind of structure has never been constructed before. So together with Ashwas Raman and Lin Xiaozhu, who is reflected in this mirror here, and that's our sample, we constructed one of these samples on an 8-inch silicon wafer. The structure consists of 7 dielectric layers sitting on top of silver. And these dielectric are made of hafnium oxide and silicon dioxide, with silicon dioxide, your common glass, being the primary ingredient. The top 3 layers have thickness on the order of hundreds of nanometers for radiation purposes, and the lower 4 layers has thickness of tenths of nanometer for reflection purposes together with silver. So if you measure the spectrum, it has a very strong solar reflectivity on the order of 97% average over the entire solar spectrum. On the other hand, it has an emission peak that's right in the 8 to 13 micron window. So we then bring this up on the roof, and this is the roof of our electrical engineering building at Stanford. So it has a flat roof, which is very nice for us. And we build the apparatus to house the photonic radiative cooler. The key point, without going into detail here, is to recognize that roof is a very hot place. And so in order to be able to do cooling on the roof, the thermal design actually is extremely important, and that we struggle quite a bit with it. But eventually, that's what we come out. So the green curve here is the solar irradiance, and it has a peak of about 900 watt per meter square hitting the sample. The black curve here is the ambient air temperature, and the blue curve here is the photonic radiative cooler temperature measured. And you can see a 5 degrees Celsius difference between the ambient air temperature and the photonic radiative cooler temperature right at the peak sunlight of 900 watt per meter square. So without using any electricity, and this is a purely passive approach, we may nevertheless generate a temperature that's significantly below ambient air. And that opened the possibility of thinking about drastically reducing the electricity consumption for air conditioning. The US actually, 15% of the building energy consumption goes into air conditioning. So being able to scale this up would be actually quite important. And that's a project that we're undertaking. This is artistic rendering, this is not real, of what the system would look like. So it would be many meters square of panel with a water loop underneath it, and to provide cold water that then can be used to drive, to reduce the electricity bill for a water-chilled air conditioning system. And that actually we are processing of realizing it, but I'm showing this picture just to point out that in many ways, in terms of form factor, this looks very much like either the solar cell or the solar thermal hot water system. But in this case, we're of course running it for a completely different purpose. So up to this point, we are constructing a structure for cooling purposes where we get rid of all the sunlight. So we're not using any of the sunlight. On the other hand, it would be great if you can combine radiative cooling with the utilization of sunlight. There are many potential applications for this. You can imagine a situation where you like to cool down your car under the sun without influencing the color of your car, for example. But here, being an audience for solar cell, I'm going to specifically talking about trying to cool down solar cells. So as I hope to show you already experimentally, roof is a very hot place, and the solar cell sits on the roof. It faces the sun, and therefore its temperature gets quite high. Typical rooftop silicon cell operates at a temperature of about 50 to 55 degrees Celsius. This has very severe consequence on the operation of the solar cell. The efficiency actually goes down as the cell gets hotter, and the lifetime also goes down very significantly. So it influences both efficiency and the cost. So it would be great if there's a passive way to cool down the solar cell. Now, by definition, a solar cell sits and faces the sun, and therefore it faces the sky. And so it will be very natural to think about radiative cooling of solar cell as well. If you look at the emissivity spectrum of a silicon, this is a typical emissivity spectrum. It has very good absorption, as you would expect, in the shorter wavelength side, above 1.1 micron or so, and that's what you use solar cell for. On the other hand, it has relatively little thermal radiation that you can use. So consequently, a silicon, in fact, is not a very good very good radiative cooling material. In order to improve its radiative cooling capability, what you would like to do theoretically is to imagine a structure that has an emissivity spectrum that looks like this. It will have the same emissivity spectrum as silicon. So you put something on top of silicon without affecting the solar absorptivity, but you drastically boost the emissivity on the 8 to 13 micron window. And in order to do that, we perform the following experiment. So we compare 3 samples. The first sample is a bare silicon structure, and this is a 525 micron thick silicon with a 75 nanometer silicon nitride layer, and with a back mirror. This is a wafer that people usually use as a starting point for constructing a solar cell. What we then do is to compare the performance of this cell, this structure, the solar absorber, with 2 other structures where we keep the silicon part to be the same, but we put additional layer on top of it. In one case, we put a 500 micron thick silica layer, and in the other case, we put a 500 micron silica layer with a photonic crystal. So what we do is we use photolithography and introduce a periodic array of air holes into the silica layer. The periodicity here is about 6 micron because we're trying to control thermal radiation here, which have the long wavelengths. We then compare the optical and thermal properties of these 3 structures. So these are the spectrum, the absorption spectrum of the 3 structures, both on the solar side as well as on the thermal side. On the solar side, in the short wavelengths, visible and near infrared, the 3 structure actually has very similar absorption characteristic. In fact, the photonic crystal structure with silicas with holes actually have slightly higher solar absorption compared with the other structures that we have there by about a few %. On the other hand, the thermal side of the spectra are very different. The black curve is the silicon thermal radiation spectrum. As I mentioned, it has very little thermal radiation, relatively speaking. The blue curve here is the absorption spectra of the thick uniform silica layer. It has a greatly enhanced absorption, but because there is an impedance mismatch between silica and air, there's actually a strong reflection as well. And consequently, there's actually a very large dip in the emissivity right in the transparency window of 8 to 13 microns. So a thick piece of silica is actually suboptimum as far as radiative cooling is concerned. The red curve here shows the photonic crystal sample. In this case, it has near unity emissivity over the entire far infrared wavelength range. And so what we have constructed here with the photonic crystal actually is a visibly transparent black body, which is a somewhat unusual concept if you think about what your mental image of what a black body should look like. So we then do the rooftop experiment where we compare these samples. So in this case, we tilt the sample to face the sun so that they're about close to 1,000 watt per meter square sunlight hitting the structure. And both the planar silica structure and the photonic crystal structure has much lower temperature compared with the bare silicon structure. The temperature difference here can be as large as 13 degrees Celsius. This is an experiment where we're really trying to prove the fundamental potential here. So we cut down the convection by using a polyethylene film to cover the surface of the apparatus. On the other hand, in this particular case, because the sample temperature is higher than the ambient, one can actually combine radiative cooling with more conventional one, for example, with convective cooling. So to demonstrate that, as a simple experiment, we just take off the polyethylene film as a cover. And as we do that, the temperature gets a lot more noisy because the wind blows through the sample, so the temperature fluctuates a lot more. But nevertheless, you still see very significant temperature reduction comparing the photonic crystal sample with the bare sample. In this case, the average is about 5 degrees Celsius. A temperature difference of about 5 to 10 degrees Celsius actually can be rather significant. A 10-degree Celsius temperature drop, for example, would translate into approximately a percentage point improvement in silicon solar cell. So we do think that there is actually very interesting potential through this demonstration of combining the utilization of sunlight with the manipulation of thermal radiation. So in the very last part of my talk, I'm going to report on some of the new projects that we've been undertaking with the support of GCEP, and that's to re-examine the nighttime radiative cooling. But in this case, to push to the limit and to look for the possibility for harvesting power at night. So I would like to show you some of the latest results where we're trying to push the limit of nighttime radiative cooling. Again, we start with the state-of-the-art, and the state-of-the-art has a temperature difference, temperature reduction of about 10 to 15 degrees Celsius at night. And this is usually accomplished by using a black emitter, a standard black body as an emitter, like a carbon black. Now, it is important to realize that even at night, a black body emitter is not ideal for radiative cooling purposes. So the blue curve here is the simulated transmission spectrum of the atmosphere at Stanford. So it's right here. And it basically, again, has a high transmission window of 8 to 13 micron, not as high as where Hawaii is, but still a very high one. If you imagine that you have a black body radiator, that black body would radiate outside in the 8 to 13, radiate heat outside of the Earth in the 8 to 13 micron window, which is great for cooling purposes. On the other hand, in the wavelength range where the atmosphere is not transparent, for example, somewhere around 6 micron, the radiator in this case behaves as absorber and absorb downward radiation from the atmosphere. And that will be a heating purpose. That will be a heating mechanism. So consequently, even at night, if you would like to get to high-performing structure, you would like to go beyond what people have traditionally used for cooling purposes in terms of using a blackbody emitter. And instead, you would like to have an emitter that looks like this, which essentially has very high emissivity in the 8 to 13 micron window, but almost nowhere else. And this, if you look at theoretically, indeed can give you very large performance gain. And this is assuming an ambient temperature of 20 degrees Celsius at night, a transmission spectrum that's similar to Stanford, and you compare a blackbody emitter to the ideal selective emitter that I just showed, and you plot that, the temperature reduction that you can get as a function of dew point that measures the water content of the atmosphere. So what you see is that over a large range of dew point, the blackbody emitter will give you somewhere on the order of 10 to 20 degrees Celsius, which is consistent, reduction from the ambient, which is consistent with the experiment that we have carried out. On the other hand, you can have a much larger temperature reduction, sometimes on the order of 50 to 60 degrees Celsius below ambient, by switching into a blackbody emitter. So you can actually get extremely cold passively with these kind of structure. So I talk about the importance of using a photonic design in order to improve the emissivity spectrum. In addition, a very important consideration in order to go to ultimate performance is to suppress the parasitic heat leakage that the environment may put on the emitter. And here is a comparison of the blackbody emitter, which is shown as the solid line, and the selective emitter, which is shown as the dashed line, for different parasitic heat leakage. In a typical parasitic leakage parameter, 8 watt per meter squared per Kelvin, which is what many of the conventional apparatus typically have, the temperature reduction between the black emitter and the selective emitter is actually very, very small. On the other hand, if you can very substantially suppress the parasitic heat leakage, then the difference between the blackbody and the selective emitter will be extremely substantial. And again, we are talking about potentially at Stanford on the order of minus 50 degree, or 50 degrees Celsius reduction from the ambient air temperature theoretically. So with that as a theoretical guidance, we then set out to carry out some experiment. And this is the emitter design that give us a peak in the 8 to 13 micron window and suppress the emissivity elsewhere. And it actually have very broad angular range, which is essential because we want to use as much emission as possible. To cut down the parasitic heat leakage, we adopt a design that looks like this. And this is a vacuum chamber. We use vacuum to cut down the convective loss. We use a radiation heat shield to cut down the parasitic back radiation from the surrounding. And we design also all the conductive pathway carefully in order to cut down the conductive heat leakage. So, and this is how the chamber actually look like. So this is the outside view of the chamber, and this is the inside view of the chamber with the selective emitter sitting there. And then we bring it to the roof at night and do our test. So in our preliminary test, we actually get a temperature that's about 27.2 Celsius below ambient air temperature, when the ambient air temperature is around here, is about 15 degrees Celsius. So this is a temperature that's about, in essence, minus 10 degrees Celsius in a summer night at Stanford. So you can really get fairly low temperature here. Now, it will be interesting to put this experimental number in a theoretical perspective. And again, this is the theoretical curve that we draw. These are ideal case of a black emitter and a selective emitter. So our experiment sits here, which actually compares quite well with what you expect from a selective emitter. So we have some parasitic loss, and we're not ideal emitter, so the temperature is slightly higher, but it's roughly speaking on the curve. Now, it will be interesting to compare this with the world record in radiative cooling that was done a long time ago. They were able to get to a temperature reduction of about minus 32 degrees Celsius below ambient. But what they have to do is actually to go up to a particular mountain that has extremely low dew point, and therefore the air is extremely dry. On the other hand, judging from the theoretical curve, what we are already seeing is even without going into the top of the mountain, just in places like here in the densely populated area, there is actually a potential to beat the record in terms of temperature by a significant margin, even with the atmosphere condition that we have here at Stanford. So we think that actually is quite exciting because it proves some of the fundamental physics of radiative cooling, especially in terms of the use of selective emitter. And also, a large temperature gradient can be very interesting for power harvesting purposes, because with temperature gradient, you can harvest power out. And so, and that produced perhaps a possibility of doing 9-time power harvesting with actually substantial energy density or power density if you compare that with what other ambient power harvesting techniques that's available out there. So with that, let me briefly summarize by acknowledging the people who did the work, especially Ashwath Raman, Lin Xiaozhu, and Zheng Chen. Zheng Chen is the postdoc that has been supported by GCEP in really on the nighttime radiative cooling side. So with that, let me stop and thank you for your attention.
Yes, question over there.
Yes, thank you very much. Very exciting. You mentioned watts only in one slide, and it went by too quickly for me to really absorb it. But I was trying to, all the way you were talking, I was trying to analogize temperature difference in voltage and then throughput, flux, heat flux with current. And what happens when you start to draw heat flux off that temperature difference? How much power can you really harvest?
So I guess in the daytime cooling experiment, I didn't go into detail because I don't have that much time. We measure what's called a cooling power. And because the thing has a temperature lower than the ambient, you can put heat load on it to bring its temperature back to the ambient. That measures what's in the literature called the cooling power. In that experiment, the measured cooling power during the day is on the order of 40 watt per meter square. At night will be a lot larger. I think you may expect somewhere on the order of 80 watt per meter square or something.
That would actually be consistent with some experiments in the Kansai region of Japan using ordinary selective surfaces to cool the high and medium temperature cases in a supermarket, and that worked fine. But it's interesting that even without selective surfaces, I was looking at your graphs, the ancient Shahs of Iran would get sorbet made for them by putting a saucer of water at the bottom of a deep well where it could see only the -40 sky and not the scattered solar radiation. So just the simplest passive actually finds this a very useful resource if you're the Shah.
Right. Oh, absolutely. I think nighttime, you mentioned a very nice example. Nighttime radiative cooling has a very long history. And the typical performance that people get at night is somewhere close to freezing temperature. Our contribution here is to point out that you can do it during the day. The Shah certainly didn't do that. They wish, I guess. And also at night, you can push this much, much further than people have done.
For your PV cooling system, the design works very well for a back contact cell. Have you given any thought to how you would be able to structure this taking advantage of silver on the front?
So I think it would be very interesting. The key challenge is really to make sure that the thermal contact or to reduce the thermal resistance between the front layer and the cell. So certainly I completely agree with you with a back contact cell where if you have a entire front surface to play with, it would be great. But I imagine that you can similarly imagine maybe a conforming surfaces on the front contact cell for cooling purposes as well.
Other questions? So I have a question. So for some of your experiments, you isolate the convection effect. So in the real system, how much convection will contribute to this either heating or cooling compared to radiation?
If you are talking about below ambient, if your objective is reach below ambient air temperature, then you need to very strongly suppress the convective effect. So even in the early experiment, we use a polyethylene film to cut down convection. For some of the cooling where the operation temperature is above ambient, you actually don't care. So the solar cell cooling, for example, you don't need to cut down convective at all. But if the objective is to get below ambient, then that's very important.
Yes, one more question.
So do you have to face the sky, or you can face anywhere which has the thermal emission which is less than the ambient, or some material in the ambient has less emission?
You need to face something that has a temperature colder than the object that you are trying to cool. So the sky is the most natural one. And I think, in fact, in many situations, if you have a low cloud, for example, the radiative cooling would be significantly affected because the temperature of that cloud is not very low. Okay.
Last question, over there. Yeah. There. Yeah.
I was just recently told that there's a desert in India where the temperature gets to 140 degrees. And it's a good place for solar concentrating collectors, but it's really hard to cool things there. I wonder if there's some possible application here.
Absolutely. I think it is actually a very interesting way to think about it, because this thing usually works best at the location where the solar cell also works best, which is where the sky is clear. The sun, of course, comes through, but then the heat can go out. So it's very interesting to look into this combination. We have actually quite a bit of ideas about it.
Due to the time limitation, we'll carry the discussion after the session. And thank Professor Shanhui Fan again for his interesting talk. So I'll introduce the third speaker, Professor Mike McGehee. Professor McGehee is in the material science and engineering at Stanford University. He is the GCEP research team leader in the area of solar photovoltaics, and he had led a total of 7 GCEP research efforts, including his current project on novel inorganic organic perovskite for solution processable photovoltaics. His research interests are patterning materials at the nanometer length scale, semiconducting polymers, and the solar cells. He received his undergraduate degree in physics from Princeton and his PhD in material science from University of California at Santa Barbara. And Mike McGehee won the 2007 Material Research Society Outstanding Investigator Awards. He is also a technical advisor for a number of companies. Without further ado, Professor McGehee. Yeah.
Okay, good afternoon, everyone. So first of all, I want to thank GCEP for giving us this opportunity to work on perovskites. you can see that a few years ago there were only 2 papers on perovskite solar cells. And when the third one came out, I got really excited about this. And with the GCEP funding, Hema Karunadasa and I and our groups were able to get started right away. And you can see that since then, things have exploded in the international community, and the efficiency in a few years has gone from a few percent to a little bit over 20% efficiency. So I'll tell you what we've learned about these materials in the last few years. This slide shows you the crystal structure of the unit cell of the perovskite, and it usually has lead in the center, but sometimes people put tin in there. And here there's an octahedral cage of iodine around it, but you can replace that with bromine or even chlorine to increase the band gap, which turns out to be important for solar applications. There's an organic cation out here, methylammonium, and that too, you can change the size of that, and you put in other components and fine-tune the band gap. And sort of the main points of what we now know about the material, we can either solution deposit it, or spin casting it, or we can spray it, or we can evaporate it. And you get a polycrystalline film, and in a lot of ways you could think of these solar cells as being like ones made with cadmium telluride or copper indium gallium selenide. It's, but it absorbs extremely well. It's a direct band gap material. It actually absorbs a little bit better than gallium arsenide, which is the material used to make the world record single junction solar cell. The charge carrier mobilities are about 10 to 30 centimeters squared per volt second. So that's not quite as good as silicon or gallium arsenide, but very respectable for a polycrystalline material, and good enough to make a highly efficient solar cell. The voltage you can get is very respectable. The voltage of any semiconductor, it depends on the band gaps, so a good figure of merit is to take the band gap energy and subtract the charge of an electron times the open circuit voltage. Gallium arsenide is the best at about 0.28 volts, and here this is 0.38 volts. Cadmium telluride has been optimized for about 30 years, and it's more like 0.5 volts. So recombination is very slow in these materials. Carrier lifetimes are over a microsecond, which is remarkable for a very strongly absorbing material, because usually if a semiconductor absorbs well, it also emits very rapidly. There's very little surface recombination. We've not yet been able to measure it because it's just so low that we can only say that it's lower than 65 centimeters per second. Gallium arsenide would be like 100,000 centimeters per second. So in some ways, it's like SIGS or CAD-TEL in the sense that it works well when it's polycrystalline. In other ways, it's actually a little more like gallium arsenide in the good sense, but it doesn't have the bad property of gallium arsenide that in gallium arsenide grain boundaries lead to recombination, and here they're not that much of a problem. So far, that's all good news. I would say the next category here is probably not good news. We did some of the pioneering research here showing that the halogens can move around in these materials, and when you have ions moving in a semiconductor, you can't maintain an electric field inside there. When there are mobile ions, they will migrate to the surface until they screen out the electric field. And it takes a few seconds for that to happen. And that means that when you turn light on one of these solar cells, the current will be changing for a few seconds. And that makes the IV curves hysteretic. And so one has to take care to get an accurate measurement. What exactly that means for long-term stability, we're still not quite sure. It may not necessarily be a problem that, that these ions screen out the electric field. They may stay there. They may not continue to move towards the metal electrodes. But if they do, like for example, if you use a silver electrode, iodine can react with that, and then that becomes a permanent degradation. We now know that if you heat these films at, say, 80 degrees, even in a dry atmosphere, and wait overnight, you will no longer have methyl ammonium lead iodide. You'll just have lead iodide because the methyl ammonium will leave the film. But we've also learned that if we cap the film and the methyl ammonium has nowhere to go, then it will stay in, and then the material is very stable at that temperature. So sealing these devices will be critically important. And I think we'll want to do that in layers. I think we'll want the electrode itself to be impermeable, and we've had good progress with that. We've made devices recently that are stable at 150 degrees as long as we use an impermeable top electrode. But the packaging will also have to be very high quality. I didn't even put it on the slide, but the perovskite is a salt, so if it sees moisture, it will take up that moisture, and then it'll no longer be the semiconductor that has the properties we like. So we absolutely can't let water get to the interior of the solar cell. And I'll just add that tomorrow, Becky Belisle will give you a 15-minute talk on device modeling of these devices and sort of show you what the implications of all these numbers are with a numerical device simulator. Okay, so I'll show you a couple slides of work mostly done in Hema's group. I just mentioned how one of the problems with perovskites is they're not stable to moisture. And to attack that, and for some other reasons as well, she's modified this three-dimensional perovskite where you have the octahedral cages touching each other in all three directions, and made a two-dimensional compound where there's an organic component that separates some of the layers. And when we look at the X-ray diffraction of these films over time after storing the films in air, we see no change. In contrast, when we do that with the three-dimensional material, water gets in there, and it also assists the methyl ammonium leaving, and lead iodide forms. And so this compound is quite a bit more stable. And right now we can only get a few % efficiency with it, but you could imagine modifying the composition of that molecule there, and perhaps getting a material that transports charge well in all three directions, and then you could have an efficient device that is also stable. Hema's group has also observed that if you take a film of methyl ammonium lead iodide and expose it to bromine gas, in just a few seconds you can switch it to the bromide compound, or if you expose it to chlorine, you can switch it over to the chlorine compound. And don't know that that's necessarily useful for solar cells, but it's very cool, and just gives you an idea of how easily the halides can move around within these films. Okay, now I'll switch gears and tell you about the research we've done in making tandems that's supported by GCEP, but also by the Department of Energy Sunshot program. There's a lot of layers in tandem solar cells, and it takes a lot of people to build them all and make the whole structure. And Colin Bailey has been the lead graduate student that has coordinated all of this and made it happen. But we've collaborated with Michael Gratzel to learn how to make good perovskite cells, and we get our silicon solar cells from Tonio Buonassisi at MIT, and we get our SIG solar cells from Rommel Newfie at NREL. And basically, when I think about where the solar industry is going and when I think about the primary role of academia, in 5 to 10 years, people are going to want modules that are 25 to 30% efficiency. And to hit levelized cost of energy targets of 2 to 3 cents, which would really make solar highly competitive, I believe we'll need those efficiencies so that fewer panels can be installed to get the same amount of power. And so indirectly, by raising efficiency, we're even targeting installation costs. And I believe the most practical way to do it is with a tandem. And here you see a plot of efficiency versus the band gap of the bottom solar cell on the y-axis and the band gap of the top solar cell on the x-axis. And it shows that theoretically you can get 42% efficiency when the bottom cell has a band gap of 1.1 electron volts and the top cell is at 1.8 electron volts. And the basic idea here is simply that this top cell is harvesting the high energy photons, the visible ones, and it's generating a higher voltage than you could do with just the lower band gap cell. As it turns out, silicon and SIGs have a nearly perfect band gap for this application. And that's great because silicon especially already has 93% of the world's market. There are factories that make panels with silicon solar cells. And so I'm not here today to tell you how we're going to shut down silicon. I'm here to tell you how we're going to add layers onto it to boost the performance of these panels. With the perovskites, we can tune the band gap with methylammonium lead halides from 1.6 electron volts all the way to 2.3 by gradually replacing the iodine with bromine. And so we can get exactly the band gap that is optimal for these tandems. Unfortunately, Eric Hoek discovered that mixed halide compound is not stable. Here you see photoluminescence spectra collected over time. And in just a matter of a minute or two, we find that the material under light undergoes a phase separation, which is another thing that's scientifically cool but kind of annoying technologically. It turns out it can lower the energy of the material in its excited state by separating into a low band gap phase and a high band gap phase and sticking all the charge carriers into the low band gap phase. So here all the light comes from the low band gap phase. So we won't be able to use that compound, but fortunately in the last couple of weeks we've discovered another compound. I'm not quite ready to say what it is, but it has a good band gap and it is stable thermally and stable under light as well. So when it comes to making tandems, we've taken a couple of approaches. Sometimes we stack two cells on top of each other mechanically. Some people call it a 4-terminal tandem. Other times we build a monolithic 2-terminal tandem. In a lot of ways, the 2-terminal is easier to use. It would be easier to build a panel. There'd be very little changes in how the panels are put together. But there are some advantages to the 4-terminal structure. With 2-terminal, you have to match the currents. If you can't do that, then the cell with the lower current will hold back the current of the whole stack. You don't need to have current density matching when you do a 4-terminal tandem. It's certainly easier at the prototyping stage because we only needed one silicon solar cell from MIT and one SIG solar cell from NREL, and we could keep reusing them. When we build 2-terminal tandems, we're using solar cells as our substrates, and we can go through hundreds of them pretty quickly. So we started with the 4-terminal, and earlier this year we published a paper showing that we can take a 17% SIG solar cell, and that would be, that's not a world record, that's more like what SIG solar cell companies can manufacture at scale. And we can take that and boost it to about 18.6%. But note that our perovskite cell was only about 12.7% efficient. When we did this a little more than a year ago, we didn't yet have a good procedure for making the perovskite cells here. Other people are hitting 20%, and we don't see any reason why our semi-transparent electrode would be incompatible with their device. And if we could gather everything that's been done in various labs around the world and get it all working in the same stack, we'd be at about 23% for the tandem today, and of course hope to do better going forward. With MIT, we made the two-terminal tandem, and Tonio Buonasisi's group took the lead in making tunnel junctions on top of silicon. On the band diagram on the right, you see that what we do is very sharply switch from highly doped p-type silicon to highly doped n-type silicon. And when you do that, you create this tunnel junction where electrons and holes can tunnel through the barrier and recombine in a good way that allows you to pass current from the perovskite cell into the silicon cell in a way that you add the voltages of the two devices. And in research, some things take years to work and other things work the first time. This was one of those things that it just worked perfectly the first time, exactly the way it was supposed to. We were able to move on to building the top layers. This is a picture of the solar cell, and it's a 1x1 square centimeter device. And our series resistance is low enough on our silver nanowire transparent electrode that we can make a pretty decent sized device with no metal grid lines running through the center of it. We only have about 13.7% efficiency right now. Here you can see the quantum efficiency versus wavelength broken down into different components. And from integrating that, we know how much current the perovskite cell can produce, and we know what the silicon cell can produce. And the perovskite is not keeping up with the silicon cell, and that's why we're at this relatively low efficiency of only 13.7. And the real problem is that gray up there, which is parasitic absorption. And if I go back to a device schematic here, that layer there, spiroometad, that's meant to transport holes, it's absorbing way too much light, and that's our problem. And normally when people make perovskite cells, they come in from the other side and the light doesn't go through the spiroometad, but we can't do that. Our light has to go through the perovskite cell first and then the silicon, and so we're getting killed there. But that is a solvable problem. We're using 470 nanometers of it, and that's because our perovskite cell is rough, and we don't want the perovskite to touch the metal electrode. So we just need to make that layer smoother and then use less of this material. And also there are other materials that would absorb less light. And when we fix that, I think we'll see some pretty dramatic improvements to the efficiency. Here I want to show you some modeling of where we believe these tandems can go in the fairly near future. This is not theoretical thermodynamic limits, not the Shockley-Queisser limit, more of just some practical calculations of what we should be able to do. So right now our band gap for the perovskite is 1.55 electron volts. If everything was working right, the optimal band gap would be 1.74 electron volts. And I think we now have a compound that can go close to that. And if the drop in voltage from the band gap down to the open circuit voltage can be maintained at 0.37 volts, then that means we would be able to get 1.37 volts for this device. We think that you can get essentially 100% internal quantum efficiency in these devices, but you probably lose about 10% of the light going through the electrode, which is not truly transparent. And with that, we think the current could be about 18 milliamps per centimeter squared. We already have fill factors of 0.77. So we think it should be possible to, with that band gap, to get about 19% efficiency, hopefully on the time scale of 2 or 3 years. And I don't know that my group could do it all by itself, but with all the groups around the world, I think there's a pretty good chance that that will happen. And if you put that cell on top of a multicrystalline cell, of course, its current is going to go down considerably because almost all the visible photons will be absorbed in the perovskite. And so here we're choosing to do this not at all for world record multicrystalline, not at all for world record silicon, but for the multicrystalline silicon that China is manufacturing at 10, 20, 30 gigawatts per year now. So these are factories that are already built. What would happen is the current would drop from 38 milliamps per centimeter squared down to 18. The voltage goes down just a tiny bit when you reduce the current. Fill factor actually goes up a little bit when the current goes down because you don't drop as much voltage across the series resistor. And so we think in the tandem we'd get about 8.5% just from the silicon. And so you add that to the 19 from the perovskite, and we think 27% is very doable. And then, of course, well, the theoretical limit is 42%, and you go to numbers in between those ranges when you use higher quality silicon, like single crystal HIT cells, for example. That's the efficiency side, but it's also important to look at the economics. And at NREL, Mike Woodhouse leads a team that talks to companies all over the world, and he gets all kinds of cost numbers. He knows what glass costs, he knows what the edge seals cost, he knows what materials costs, he knows how much it costs to evaporate things, sputter things, spray things, laser scribe things, and so he can cost project these sorts of things. He loves creating these flowcharts. He absolutely will not let us do any calculations until we have one of these color flowcharts that you see here. And I guess the point is that we really do include just about everything. And this has been checked out, for the mature technologies, and they know that their numbers are pretty accurate. And we should be able to publish this within the year, but I'm allowed to show these results as long as I tell you that it's an ongoing draft analysis. And a lot of these costs we get from cadmium telluride panels. And so you see like how much the glass is, and over on the right you see how much putting just putting the whole module together and having the junction boxes. And it's those costs alone that show you why efficiency is so important. And then in the center, you see the costs that we're thinking it will be for the perovskites. And the bottom line is that it should add about $14 per meter squared if you already had a silicon panel and you're adding these perovskite layers to it. And so if we look at multicrystalline silicon, which today is something like 50 cents per watt, and the panels are 16% efficient, or you could also look at $82 per meter squared, we think we'll add 13, taking it to 95. And maybe we're not quite fair on efficiency. Their 18% cell made a 16% module, so our 27% cell would probably be maybe a 24 or 25% module. But we would have numbers something like 0.34 to 0.38 dollars per watt. So we would have a net reduction, and then you would also see installation costs go down because of the higher efficiency. And again, that's just with multicrystalline silicon. With higher quality silicon, our cost number would go up, but our efficiency would go up as well. And so that's the vision. That's what we're working hard towards and bringing all these pieces together. Didn't say a whole lot about stability, but of course we're working hard on that, and I'm pretty confident the cost and the efficiency can be done, and stability is going to be our main issue in seeing if we can get the 25-year lifetime. So thank you all for your attention, and I'd be happy to answer your questions.
So we'll have time for a couple of questions. Yeah, over there.
So you consider the multi-junction solar cells. Have you ever considered about using it as the concentrating solar? And you actually condense the solar radiation and shine on each of the cells to look at their performance.
Right. So I wouldn't recommend using these panels under a concentrator. If you're going to pay the money to use trackers and concentrators, then and you're going to have a tiny solar cell, cost is less important. Efficiency is extremely important, and you'd probably want to use a 3.5 system that would be over 40%. Also, I'd be real concerned about having the temperature of these approaching 100 degrees. I guess you'd want to have extremely good cooling, but it doesn't make a whole lot of sense to push so hard to get the costs low on a per area basis if you're planning to use a tracker and concentrator. And yeah, we do have ways of probing these cells individually. It's probably best talked about offline, but there are ways to get the quantum efficiencies of the different layers separately.
Another temperature-related question over here on your left. How does temperature affect the performance of this tandem cell compared to a silicon cell?
We measured the temperature coefficient for the first time just in the last week, and it's not as good as we expected. You expect high gap materials to have very impressive temperature coefficients, and I'll just say it's not quite as good as we expected, but I don't want to put out extremely preliminary numbers that we just literally measured it one time last week.
Maybe one last question? Any questions? If not, let's thank Professor McGehee again for the wonderful talk.